Hi, I'm Joe Chase, and I'm going to walk you through this uh, Module 3 quiz. And to be honest, the material in Module 3 is some of the most challenging material that we have in the semester. So it has to do with Newton's laws, but it also incorporates vectors. And then some of the algebraic skills needed can be a little complicated. So we'll see where we have to solve two unknowns with two equations. So and just be prepared for that. There are also, uh, if the algebra is a little bit rusty, there are also two equation solvers that you can find online. So once you get them set up correctly, you just enter the coefficients and it'll tell you the answer. So totally legit to use. All right, I'm going to share my screen and we'll take a look at the questions that we have. So I have Canvas set up as a student view, and here we go. So module 3 quiz, Newton's laws, check. All right, take the quiz. Let's go. So this is just two questions, but they're pretty involved. So it looks like I'm gonna have to leave student. There we go. Okay. And let's take a look at this one. So mountain climbers, rope teams. A group of mountain climbers is walking along a snowy horizontal ridge. The lead climber thinks they're on solid ground, but it turns out it's a nice bridge over a crevasse. Scary. Okay, and then we have a lot of stuff to figure out. But really, the bottom line is that we're either going to need to make some assumptions, like the number of climbers and their average mass. And here, um, I'd like you to choose more than two climbers. And I'll set up an example that does just have two climbers so we can take a look at what the uh, issues are at hand. So I'm going to stop sharing and then we'll go back and take a look at my document camera. Okay, well, let's go ahead and do a diagram. That's always kind of helpful, right? So here's our cliff. And my physics world is a stick figure world. So we have a stick figure trying to hold on to their friend who's hanging from a rope, something like that. So to keep things simple, I have a vertical rope here and a horizontal, well, pretty close to a horizontal rope right here. So we have two climbers, and I will assume that each one has a mass of 100 kilograms. You could make them different masses, but it's going to be hard enough. So, um, in this situation, so the person is digging in their heels, and we're also supposed to find out. We're supposed to try and figure out the minimum coefficient of friction that's needed, and then the tension in the rope, and then a couple of other things. So we'll just set that up really quick and see how that works. So let's pick a coefficient of friction. It is icy, but maybe they have crampons that are digging into the snow. So let's assume that we have a coefficient of friction of 0.6. So what a coefficient of friction does is really, it means that the force of friction is proportional to their weight. So that's one of the things that we recognize is that um, we oftentimes, when I'm doing a lot of work with forces, I'll abbreviate it symbolically as a force and then use a subscript to indicate what kind of force we're talking about. So since this is a force that's caused by gravity, I use F subscript G, and that's equal to mass times gravity. And now both of them have weight, but we're trying to identify all the forces that are at work. And This is often called a multi-body problem, where we have two objects, and this rope is actually a vehicle for interaction between the two. So the rope has tension, so that's an upward force. And again, since I'm running through a cast of characters here, tension, which is going to be Ft. This isn't always true. This is only sometimes true, or at least I didn't write it equal to anything because it depends on the circumstances. So we have tension pulling upward, and then we have weight pulling downward on this individual. But if this is you and this is your best friend, and you're doing a good job here, so your best friend is not accelerating. So we're going to say that the acceleration is equal to 0. And then up here, we have tension pulling this way. And this person also has weight. And they're also feeling a force that's pushing them upward, which is the normal force. So that's another one that we're going to add to our cast of characters, which is the normal force. And normal in this case is referring to the geometric construction, which means perpendicular. So anytime you're resting on the surface, whether it's horizontal like this or at an angle, the normal force is always perpendicular to the surface. And then, of course, we have friction, and that's what's keeping this person from moving is the force of friction. So then I can write another one. So this is 4 forces at work here. Now, these forces will change depending on the circumstances you choose. But when there's something that's always true, that's really helpful. This is always true, and this is always true. That the force of friction is always the coefficient of friction times the normal force. Always true. Okay, so this technique that we've done where we've isolated the forces that are acting on each object is called free body diagram. And we can identify all the forces and also the state of its acceleration. So let's give them names. Let's call this, this is sort of our hanger, or our victim. That's kind of depressing. Let's call, yeah, let's just call him the hanger. So the hanger has a free body diagram, and we can always start off with F net equals ma. That's Newton's second law. Now, F net is not a force by itself. What it is it's a reminder that we should add all the forces that are supporting each other, and we should subtract forces that are in opposition. So it's really, this is telling us to take a look at the free body diagram and then show what forces are at work here. Now, these are two vertical forces. I have tension pulling up and gravity pulling down. And so because tension in this case is vertical, I'll write a plus sign here, and then minus the weight. The weight's always equal to mass times gravity. And then write the state of the acceleration. So acceleration can be speeding up, slowing down, changing direction, or be in equilibrium. And being in equilibrium, like our hanger here, means that the sum of all the forces is 0. The forces are balanced. The acceleration 0 doesn't mean that there are no forces, just means that they're balanced. And it's extremely rare for there to ever be no forces. So that's going to be 0. And then that means that the tension has to be equal to mass times gravity. Okay, good. Now, for our friend up here, well, let's call them the hero. Yay. And same thing, F net equals ma. And now we want to identify the forces that are happening here. Now, this has just got 4 forces, 2 vertical and 2 horizontal. In a situation like this where something's resting on a surface, what we can take away from this is that the force of friction, well, we need to know what the normal force is in order to figure out friction, but the normal force is directly opposite the weight. And so for the special case of being on a horizontal surface, we can actually write coefficient of friction is mass times gravity. So this isn't always true, and this is a special case because it's horizontal. Okay, well, here we go. This is something that we came up by analyzing the vertical forces. So we don't need to do a separate equation for the vertical forces. We've kind of already analyzed that. And friction's holding us back. So that's the left. I'll call that negative. Tension is to the right. I'll call that positive. So positive Ft. And I should have really labeled the masses here. So hanger, let's call that M1. And we'll call this M2. Probably better names, right? But than hanger and hero, because I can't do FH because the other one's FH. So anyway, plus FT minus, so this is a 1, plus M2 tension minus force of friction. Sorry, I'm messing this up. Coefficient of friction times the mass of 2 times gravity. And that also equals 0 because they're not accelerating. So this means that the tension is equal to coefficient of friction times mass 2 times g. Okay, so what that does is it leaves us with a dependency on what the force of tension is. So we know that both masses are 100. We know that the coefficient of friction is 0.6. And we also know what planet we're on. So that means we're ready to solve this. Now, I made the assumption that we had a coefficient of friction up here. But now when I set these two equal, I'm realizing something else. If these two have to be equal, then M1 times G has to be equal to the coefficient of friction times M2 times G. So this actually puts a condition on it, on the coefficient of friction. So gravity's on both sides of the equation, so they cancel. And for the case that their masses are the same, this means that the coefficient of friction has to be equal to M1 over M2. So in this case, it has to actually be equal to 1. But if I had more hikers out here, then I could get away with a smaller coefficient of friction. All right, so that's a good starter here for this question number 1. It's a big one here. Let's take a look at the other question, which involves a plane. So I'm going to share my screen really quick, and we'll take a look at what that looks like. So there's a video to watch. And in the video, you'll see that there is a pendulum set up, and the pendulum swings backward as the plane accelerates. And the acceleration for those aircraft typically is fairly constant, although vibrations makes it jump around a little bit. All right, so having done that, let's go back and take a look at our prompt. So this is quiz question number 2. And we have a pendulum that normally would hang straight down, and then the tension would just be equal to the weight. But now, because there's acceleration in this direction, then the pendulum bob does this. Now, if you're on an aircraft, you can actually, most phones, well, not most, all phones have an accelerometer built in. And you can definitely get an app that can measure the acceleration in all three axes, so X, Y, and Z. Now, the reason why the pendulum bob swings back in the first place is that when you're in the aircraft, you have the force of the seat is what accelerates you forward, right? So you feel pressed back into your seat because your seat is pushing you forward. But this little pendulum doesn't have anything to push it forward. So it starts to lag behind you. It falls behind. But as it falls behind, you can see that there is a component of the tension. So here's our tension, Ft. And since the tension is no longer vertical, we have a component that's available to help accelerate it forward. So we still have gravity. And so we're going to have a component along the x-axis. So we could call this Ftx, and a vertical component that we could call Fty. So this is not a two-body problem. This is just a one-body problem, but it does have two-dimensional components of vectors. So we have to break this up into its x and y components. And I'm a big fan of using a table. So if you've seen some of my other note videos, you'll recognize this technique where we're going to have a table that has the x components and the y components separated. Because that's the only way you can add vectors is by their x and y components. And the two players in this are tension, so Ft and gravity. And then when we add them together, that's going to tell us what the net force is. So there's our table. Okay, what about angles here? Well, let's say that I have an angle here with the vertical. And I have an angle with the horizontal. I could use like a symbol for like phi or theta or some uppercase theta, but let's just call it V and H. And then that's going to be this part right there. So it would be the case that theta V plus theta H is constrained to be equal to 90 degrees. Now, there is no acceleration vertically, but the object is accelerating to the right. So when it's time to do FNet, we could use those two conditions to help guide what's going to happen next. And so along the x component, the sum of the forces has to be equal to ma. Along the vertical, the sum of the forces is zero because there is no acceleration up and down. Now we can take a look at the rest. So T is the one that has components that are along the x and y direction. So the x component is going to be equal to Ft times the cosine of theta h. And its y component is going to be Ft sine of theta h. You can see that if there was no acceleration, it'd be hanging straight up and down, and then theta h would be equal to 90 degrees, and the sine of 90 is 1, and the cosine of 90 is 0. So there wouldn't be any horizontal component. Then the tension would just be equal to the weight. But now the tension has to be more than the weight because it's doing two things. It's keeping it from falling, and it's also getting it to accelerate. All right, now let's take a look at so gravity. Gravity is downward, so minus mg, and gravity doesn't have a component along the y component. So that's equal to, oops, this is 0, and this is minus mg over here, okay. All right, great. So now from the x equation, I get ft cosine theta h equals ma. And from the y equation, I get ft sine theta horizontal is equal to, or minus mg equals 0. Okay. So we're almost crossing the finish line here. And, but it's kind of unique, right? So let's write these equations again one more time. So I have ft, which I don't know, times sine of theta h equals mass times gravity. And then I have ft cosine theta h, which is equal to ma. So what we're supposed to walk away with is a relationship between the angle and the acceleration. Now, this again, different techniques for two equations with two unknowns. So here's one technique where we set the two equal to each other. So that's a technique. In this case, I can't really do that because they don't equal the same thing. But what we can do is divide one equation by the other. So I'm just going to put a divide by symbol here. Because if the numerators of two fractions are equal and their denominators of two fractions are equal, then the fractions are equal. So just kind of cleaning this up, this is going to be ft sine theta h over ft cosine theta h is equal to, I'm really just writing the same thing down, but now I'm just using one equal sign. All right. Now, there's lots of cancellation that can happen. The m's can cancel, the t's can cancel, but it's still weird, right? So I've got sine theta over cosine theta equals g over a. But don't forget that all those trigonometric substitutions, that those trig formulas that you learned way back in algebra 2, they're still happening. So sine over cosine is tangent, right? So I'll let you pick it up from there, but the tangent of the angle is equal to this ratio. So you can develop, now that there's just one trig function, then you should be able to solve for that. All right, so that's this unit's quiz helper. I hope it's helpful. And of course, feel free to drop in for office hours or send me an email. And we can always set up a personal way to chat when you're stuck on something. All right. So hope you have a great day. It's a beautiful day here in Vermont, so I think I'm going to go outside and enjoy some of that. Thanks.